So, good morning, everybody, and welcome to this Faust lecture. Just to know for myself, are any one of you familiar with Faust? More or less. Okay. So, this morning I'm going to give a kind of philosophical presentation of Faust. And this afternoon we will go more deeply into the code and the way to program with Faust. So first of all, what is Faust? So it's what we call in computer science a DSL, domain-specific language. So it's a programming language very specialized to build electronic music instrument, audio plugins, and signal processing applications. So before explaining what Faust is, I'm first going to give you a kind of background, historical and philosophical, again, background on computers and programming languages. So let me see if I can zoom this picture here. Okay, so until the end of World War II, computers were human persons. And you see here a computer room with all these ladies doing manual computation, and when the people like Alan Turing started thinking about what a human computer is doing and what it can do, he was very inspired by these human computers. And so this is Alan Turing, and Alan Turing started by creating a kind of theoretical computer. At that time, there were computers, but there were human computers and also mechanical computers. But these computers were only able to do a particular kind of computation. And if one wanted to to do another kind of computation, he had to rebuild a new mechanical computer, so to speak. So Alan Turing started by trying to formalize this idea of what is a mechanical device doing computation. And so he invented this, what we call now the Turing machine. And then he discovered that he was able to create a universal Turing machine. A Turing machine that were able to interpret, so to speak, the description of another Turing machine. So it was universal in the sense that you just have to program it to have the behavior of a different machine. And so this is the idea of a universal computer. It's one physical machine that you can logically reprogram to do other kind of computations without having to rebuild again physically the machine. So as Alan Turing said, it was a kind of office work to program because you don't have to build physically a new machine. At the same period, so this was before the real invention of electronic computers. At the same period, Alonzo Church, this guy here, who was also the thesis advisor of Alan Turing, invented Lambda calculus. Is there anyone familiar with Lambda calculus? Okay. So, Alan Turing and Alonzo Church were able to prove that Lambda calculus and Turing machines are equivalent. And so the so-called Church-Turing thesis says that everything that is computable can be expressed as a Turing machine or as a Lambda calculus expression. So computers are a finite approximation of universal Turing machines. And this means that from at least maybe not a practical point of view, but at least a conceptual point of view, all these machines are equivalent. And so there is nothing that we could not compute right now that if you put aside the speed and size and memory size of the computer, all the computers are equivalent, even quantum computers, so to speak. Obviously, the memory size and the speed are extremely important. And, but from this point of view, all the computers are equivalent. So you are all doing computer programming, right? What language are you using? Max maybe, or essentially Max, or other languages? Yes? Fortran? Ah, Wolfram, okay. So computer programming is essentially teaching a universal machine how to behave, and for that purpose you need a programming language, which is a vocabulary and a set of grammatical rules, so to speak, to describe such behaviors. And the oldest programming language, which is still in use, is Fortran, Formula Translation, and it was designed in '75 by John Bacchus. And Fortran is still used today, and in particular for scientific computation and high-performance computing. John Bacchus is also the inventor, so to speak, of modern functional programming. And Faust is an example of a functional programming language. Who is familiar with functional programming? Okay. Are you a computer scientist? Okay. So now that we know what a computer and the programming language are, let's give a little bit of background about music programming languages. Well, here is a non-exhaustive list of music programming languages. And among the oldest one are the Music 3, 4, 5 programming languages. And today, very familiar music programming languages are Max, Pure Data, Chuck, and Supercollider, C-Sound, and Faust. But you see that there are many of them. There are always new programming languages appearing. For example, among the latest programming languages are Kronos and Soul. Have you heard of Soul? It's a new programming language developed by Broly, the makers of Juice, and it's also a compiled programming language. Okay, so Music 3 appears in the early 60s, and so the important point to understand is that if you want to make a computer, to have a computer do sound, you need a way to describe how to produce the sound. And so the Music 3 was an attempt to create this kind of vocabulary to create sounds using unit generators, which was one of the invention of Max Matthews, and that it's still very widely used. So all the modular synthesizer or languages like Max or even Faust are based on this idea of unit generators that you connect between them. So the one that was really widely used was Music 5, and it was used in particular for the early experiment in sound synthesis. For example, Jean-Claude Risset worked a lot with Music 5, and many composers worked with Music 5. So here you have an example not of Music 5, but of C music, which is closely related. And you see that conceptually it's a graphical programming language, but using a textual syntax. So you have unit generators like oscillator, envelopes, etc. And you have connections which have names to connect them together. So C-Sound is currently the current descendant of Music 5, which is also very widely used with a huge library of objects, and so I would say that most of the existing synthesis methods are available in C-Sound libraries. Another programming language, which is also very well known and more recent, is Supercollider by John Mccartney. He was open sourced several years ago when John went to work to Apple. And it's more an object-oriented programming language. And the particularity of Supercollider is that, to my knowledge, it was the first to have a separation between the audio engine, so to speak, and the programming language used to control this audio engine using OSC communications. And so it's easy to have the audio engine as a library that you can embed in some applications. It's also easy to control Supercollider from another front end, so to speak, than the Supercollider programming language. Nearly at the same period appeared Max MSP, actually, which was developed by Miller Puckett when he was at IRCAM, and later he was Max was commercialized and developed by Cycling 74, now part of Ableton. Later came Pure Data, which is an open source version of Max, also written by Miller Puckett, which is also very widely used by many. In France, for example, I would say that Max is more used than Pure Data, but maybe in Germany it's not the same case, and I think that Pure Data, sorry, it's very popular. Okay, so this was a language developed at Gram by Dominique Faubert, Stéphane Letz, and myself in '97. And, well, it was not very successful, but it was a kind of test of proof of concept, so to speak. And LOD is based on a very different approach of programming. It's very based on the Lambda calculus. And the idea is that you program by giving examples. So, for example, here you see an example of the concept of repeating 3 times something. So how do you describe this concept? You just repeat 3 times the same note, for example, and then you make variable that note to capture the concept of repeating anything 3 times. And here you see, so this is an abstraction, and this is an application. So we apply the concept of repeating something 3 times to this motif here. And here the resulting is this repetition. So LOD was based on this idea. So you don't have a programming language separate from the music. You use musical objects as programs by making them variable. So it's a kind of programming by example, so to speak. So if you want to program a canon, for example, you will start by building a concrete canon, and then you will abstract the motif that you have used for that canon to capture the structure. So it's really based on this idea of abstraction. You go from the concrete to the abstract by forgetting neglectable details, so to speak, by making variable some of these details. And then you go back from the abstract to the concrete by giving details to the abstraction, so to speak. Maybe that's not very clear, but just to mention that it was based on a completely different approach. So Open Music was developed in 1998 by Gérard Sayag and Carlos Agon at IRCAM. So it's a kind of visual programming language based on Lisp. Lisp was for years and years, Lisp was really the programming language used both for artificial intelligence and experimentation in new programming languages. So many languages for music compositions were based on Lisp. And that's the case with Open Music. But Open Music had the advantage to introduce a graphical representation of Lisp program. So, to my knowledge, it's the only example of a visual Lisp environment. Are some of you using Open Music for music composition? Okay. So Faust came in 2002. The first publication was 2002. And so Faust is a very, you will see, it's a very focused language. Really, you don't use it to make a whole piece, for example. But it was the first at that time to be a compiled language. So I don't know if you're familiar with the difference between an interpreted and a compiled language. Most of the usual programming language for music, like C Sound, Max, Pure Data, etc., are interpreted languages. So it means that you need to have a kind of runtime system that run the patch or the Supercollider program for you. When you have a purely compiled language, then you translate your audio program into machine code directly, and this machine code doesn't need any help to run on the device. So if you are not familiar, it's like, you have two types of translation: simultaneous translation, where you speak and someone translates. Obviously, it takes more time. It's very convenient, but it takes more time than if you pre-translate everything. So compiling a language is just pre-translating all the code to the machine code before running it. Another very interesting programming language is called Chuck. And Chuck was really designed for live coding. So, are there anybody familiar with Chuck? Or doing live coding? So there are many people doing live coding on stage as a kind of new kind of performance, so to speak, which is something quite fascinating because really, programming languages were not designed for this kind of usage. And so it's really an invention of musicians to do this kind of performance. And this kind of application puts a lot of constraints on programming languages. And in general, but I will present this idea later, in general, we use all this programming language as a way to do creative programming, which is quite different from the usual engineer approach of programming. Another system quite fascinating is, even if it's not clear if it's a programming language or just a kind of fancy synthesizer, it's the React table. But here you are in between controlling and programming something. And it's quite a fascinating system. Okay, just to give you some ideas, some background about music programming languages. What I would like to say is the importance of this idea of creative programming. That is to use a program as a means of invention. When you learn computer science at the university, for example, you are told that you need to specify your problem before starting to program, starting to code. Obviously, if you want to invent a new sound, a new musical structure, or a new kind of interaction, you cannot specify what you have not yet created, so to speak. So you use the programming language as a means of invention. And so that's, I'm sure that you, in your work, you are also in this mood of trying things, changing a little bit the program, etc., to discover. You don't know exactly, you have some idea, obviously, but you don't know exactly what you want to do. And at some point, you will discover that that's what I was looking for, so to speak. Sorry. So, in my view, creative programming exploits the relation between intentional description and extensional descriptions. What I mean by extensional description, for example, of a sound, is just the collection of samples of that sound. But obviously, you cannot just invent a new sound by putting samples one after the other. It's not meaningful for our mind to think in these terms. So you have to give an intentional description of this sound. That is, you have to describe how to produce the sound, not the sound itself, but the way to produce it. So there is a kind of indirection. You work on the intentional description. In other words, you work on the DNA of the sound, not on the body itself, but how to produce the body by the DNA, how to produce the sound by using sound synthesis techniques. So intentional description are described using a kind of programming language. And the role of the computer is to transform this intentional description into the actual sound, the extensional description. So all this creative relation with the computer using the programming language is on this relationship between intentional and extensional description. So basically, well, there are many things in this slide, but I like very much the model of creativity of Henri Poincaré, which is based basically on two things, cogitare and intellegere in the Latin sense. Cogitare means you put idea together, you shake it, and you produce new ideas, so to speak. And this is typically done at the subconscious level, so to speak. And this is where you start working on a problem, maybe you don't find the solution, you go doing other things, maybe you go for holidays, and maybe suddenly you have the idea. So this idea doesn't come from nowhere. It comes from your subconscious that was able to cogitare between many ideas. And the other important point is the intellegere, the action of choosing something, which is also very important. You cannot just have generating system. You have to have a mechanism of choosing what's interesting. So typically, in the way we use programming language as a creative means that we use cogitare on a program, intentional descriptions. We use the computer to transform this intentional description into extensional description so that we can listen to the sound, for example. And this is on the extensional description that you apply your intellegere to choose what seems to be interesting to you. And that's also why, for example, mathematicians will speak a lot about beauty. Because if the subconscious is able to do cogitare, it's not able to do real computations. But there must be a kind of mechanism that where the unconscious called the consciousness to say, okay, I have potentially something here interesting. And because the potentially interesting things cannot be based on actual computation, it's based on an aesthetic feeling, so to speak. So this is why mathematicians, for example, have really a very deep sense of aesthetics applied to mathematics. Because this is this mechanism that tell you this is potentially interesting. After you have to verify, do the actual computation, etc. But there must be a mechanism that where all the ideas that are cogitated into the unconscious are observed and something to select the most promising ideas, so to speak. They are maybe not right, but they are promising. And this promise is based on the purely aesthetic evaluation, so to speak. Okay, that's for this, this background. And the intention of this background was to say that it's important to think of programming language for music as something that can be easily, where cogitare it's easy. So you need to be able to easily express ideas, easily recombine ideas, etc. And so the design of Faust was very based on these ideas of cogitare intelligere. So, what is Faust used for? Obviously, it's used on stage for concerts and artistic productions. Many productions used at Graham use Faust. Again, not for the whole piece. Maybe the whole piece is written in Max, but elements are written in Faust. What's interesting with Faust is that it offers an end-user high-level alternative to C. Many, for example, if you want to program if you want to program an instrument on the phone, you have to use Java or C or Kotlin or whatever programming language, which are not mainly used or known by musicians. So Faust can be used to write this kind of things in a much more efficient way than using traditional programming languages. And all the technology behind Faust is, and in particular the Faust compiler, is used to synthesize the most efficient implementation from the description that you do in Faust. So in Faust you describe, okay, this is the algorithm of my reverb. I don't care that much of the implementation. Here it's what mathematically it should do. Let the compiler do the best possible implementation. So in that sense, Faust is a specification language. It's not an you are not in control of the implementation. And another way to say that is that if you write two different Faust programs with the same mathematical meaning, they should result in the same implementation, which is hopefully the best possible implementation. Obviously, this is very theoretical. We're not as good at that, but this is the goal and the objective. By being compiled to native code means that Faust has a sample level semantics. In Max, for example, when you don't have a sample level semantics, you have a vector level semantics. You cannot do a delay of one sample unless you put the vector size to one sample and you don't have any any more good performances. So in Faust, you have sample level semantics, and in all the modern compiled languages, you have now, like Kronos, for example, or Sol, you have sample level semantics, or even Gen in Max now. Another interesting point of Faust is that because it's compiled, you can generate code for multiple languages. So you can generate code for C++. Obviously, this was the first supported language, but you can generate code for Java, for JavaScript, and recently for WebAssembly. Who is familiar with WebAssembly? Have you heard of WebAssembly? Okay, so WebAssembly, you know that most of the programs written for the web are written in JavaScript. WebAssembly is an attempt to have a low-level, efficient programming language for the web. So it's a kind of assembly language for the web. And this is really very interesting because it runs maybe 10 times faster than JavaScript. And there is a lot of interest for people porting games, for example, from C++ to JavaScript, or to WebAssembly, to run them on the web. And this is, you will see that all the tools we're going to use to work with Faust are web-based. And it's now possible to do real-time audio signal processing in the web, thanks to two things: the Web Audio API that appeared with HTML5 and WebAssembly. You will see that it's far from being perfect, so you will not use probably web technology for concerts right now because you may experiment some glitch and clicks, etc. But it starts to be more and more usable. There are still problems to be solved, but this is really the future. So it means that using this kind of technology, you can just publish your application on the web, and you can use it. You can imagine in the future to have many reverb and synthesizer running on the web, and that you can just connect together and without having to install anything. So the other last interesting point is the fact to run code on most platforms. So the situation that we are not using anymore only computers on stage. We are using mobile devices, we are using very small boards and smart objects, etc. So our computers are more and more powerful, but at the same time, we want to program more and more small, cheap, not very powerful systems. So it's very relevant to be able to, from the single language, a single description in Faust, to be able to deploy these codes to all these machines. Are some of you interested in an embedded system or doing electronics and this kind of stuff? Okay. So Faust is very interesting from that point of view also. Let me show you some example. I'm going to show you some videos. Okay, so this is an application that I'm not going to show during the workshop, which is called Faust Live. It's an application that you can install on your computer. It works on OS X, Linux, and Windows, and it embeds a Faust compiler. So it's a standalone application that embeds a Faust compiler. So in this example, I'm writing a program here that synthesizes some wind, kind of wind instrument. And we are going to deploy using Faust Live this wind instrument on two different systems, Android phones and okay, so this is This is this very simple instrument. Now we are going to export this to the owl, which is this white pedal that we saw before. So this idea of deploying is very important in Faust. You test your program maybe on the web or on your computer, but you run it on more than 20 or 13 different architectures. So here it was exported for Android. And now we're going to see the exact same program running on the going to learn during the workshop is how you can build this kind of instrument, in particular on Android. By the way, who is using Android phones? Okay. Who is using the other one? Okay. So we have the technology also to do that also for iOS. The problem is that we are not allowed by Apple to have a compiler that generates iOS applications that you can easily download on your phone. So what we can do is to create the C++ project that you need to compile yourself. And you need to be a registered developer to do that. But for Android, we don't have this limitation. So this is why it's going to be easier for those with an Android phone. Okay, let me show you some example of embedded system. This one is quite funny, and you will see a very countryside. So this instrument is based on a teeny ARM board, very cheap, maybe 20 euros, and all the synthesizer is built in Faust using this teeny system. And it's a very, everything, all the information are available on GitHub for those who would like to replicate this instrument. And it's called Striso, S-T-R-I-S-O. Okay, let me show you, oops. Two examples of other application. There is a Californian company called Moforte that do very nice instrument for iOS using Faust, at least Faust for the DSP part, not for the user interface part. Let me show you a first one called Guitar.
This is Moforte's virtual guitar, power chord for mobile and tablet devices. What makes power chord unique is that unlike other virtual guitars that simply play back recorded samples, power chord models the physics of a real guitar. Power chord provides an unprecedented interactive playing experience using feedback, distortion, and effects. It can be strummed in different positions. The strings can be scraped. And you can even play harmonics. One of the most fun things about playing power chord is interactive feedback and distortion modeling.
interesting here is that there is no sampled sound at all. It's all sound synthesis using what we call physical modeling. So a kind of modeling of the physics of a real guitar. And what's interesting with physical modeling that it gives you a lot of opportunity to play with the model more than the more synthetic sound synthesis technique. And so it's quite a fun application. Let me show you another application developed by the same company called Moforte. The company is called Moforte, and so the first application is called Guitar, and the next one is called GeoShred. And it's quite fun also. Okay, so these applications are for iOS only. So if you have Android, you cannot run them. iOS is still superior in terms of latency and yeah, and some audio qualities like that than Android. Oops. Okay, so let's start by making some sound, not as fancy as the sound of GeoShred. So again, all the audio engine was developed using Faust, in particular by Julius Smith, which is one of the best specialists of sound synthesis in the world. And Julius is one of the major contributors to the Faust project, in particular for the libraries of Faust. And we have the chance to have very nice libraries of filters in Faust, thanks to Julius. And he told me that when he discovered Faust, he fell in love with the language and decided that whatever he had ever developed in his life, he will try to port it to Faust. So thanks again, Julius, if you listen, for that. Okay, so during the workshop, we will use this faust.gram.fr/ide, which is a tool that that embed the Faust compiler. So let me explain the technology. So everything runs using the Web Audio API, but on the client side, on your computer, when you load the page, you also load the Faust compiler. And the Faust compiler with the backend to generate WebAssembly. And combined with the Web Audio API, this allows you to run in real time audio code. Again, not without glitch from time to time, especially on my computer. I hope that on your computer it's going to be better, but okay, so can you read the code or is it too small? More or less? So let me try to zoom a little bit. Is it better? Okay. So here we have a very simple Faust program. It contains 2 lines. The first line is an import of the Faust standard libraries, where most of the filters and effects, etc., are predefined. And then you have the definition of process. Process is the entry point into your code. So if a minimal Faust program adjusts the definition of process. Okay, so what do we have here? We have a button, you see button play. You have a colon sign here, then you have a djembe model, then again this strange sign here, and here a reverb. So let me remove the reverb first. Okay, so here you have a button and the djembe model. Here you see the the graphical representation of the Faust code. So it's very useful. It's computed in real time as you type your Faust code. You see the graphical representation. So it's useful to understand what your program is doing. So note that the syntax of Faust is a textual syntax, but it has a graphical representation. So as you can understand, the colon sign here, it's a way to say, let's connect the outputs of the left expression to the inputs of the right expression. So it's a patch operation, so to speak. Typical studio operation where you connect the output of one device to the inputs of another device. To be able to do this connection, the number of outputs and inputs must agree. So for example, here we have one output for the button and one input for the djembe model. So once you have your Faust program, you can run it. Just press the run button here. And you see the code was compiled and it's now running. And you see a minimal user interface, which is this play button. Let's change the name, gioca, con due C, una, così, okay. And you see that the user interface is changed according to that. Okay, so here you see the oscilloscope view of the sound. You can see it also if you open this on a different window here, you can resize that. Put in plot mode here. Okay, so the way it displays sounds, it's quite sophisticated. For example, here you see, you can see the waveform in continuous mode, for example. Oh, sorry. Not this one. Oh. Okay, so if I run it again, sorry for the delay, but I need to reorganize my screen a little bit. I have clicks, I'm sorry for that. Okay, so you can experiment with your code like this. Let's do something which is to, here we have a mono signal. I'm going to split the signal and to feed a reverb with the signal. There is a model called FreeVerb. I can use that. So now, if I look at the interface, you see that it's different because the FreeVerb model already has its own user interface. So it's combined with our code here. And now we have the reverb. Okay. Let's do something else, which is to export this code. So here you can go on this track button, and this is the export. So when we do that, we're going to export that to whatever we choose here. So I'm going to choose OS X and Max MSP. So the code was running into your browser, but now the code is sent to a special remote compiler that runs on the cloud. And so the code is sent there, it's compiled, and you get back the Max MSP object for OS X. So if I press compile, so depending on the type of code, it takes more or less time. The longest one is when you compile for Android. It can take 1 minute, something like that. But for the other kind of targets, it's quite fast. So now I can download the code. Okay, call that binary. Replace. Should put my glasses, maybe it's better. Show in Finder. So what do we have inside? We have the binary, Max MSP binary. We have a patch to use that binary that reproduces more or less the user interface. We have the original Faust code and a small library used to do the connection. So now if I double click on the Max patch, here what we have. So the external object is this one. I'm going to connect that. Okay. And now you have the same thing, the exact same sound without the clicks now because it's running in Max. Okay, so this gives you a short overview of how you work with Faust, with the IDE. So you prototype your program, and then you can export it. Let me give you another. No, maybe I should continue on the slides. What time is it? Okay. Are you surviving? It's okay? Yeah? Okay, perfect. Okay, this was, okay, let's go back to the slides and give you an overview of the design choices for Faust. So Faust is based on a purely functional approach to signal processing. So there are basically two kinds of computer programming, functional programming and imperative programming. Now, many standard languages like JavaScript, for example, or I don't know, Python or whatever, have functional programming elements. But in a purely functional programming language, what you can do is only describe mathematical functions. So what is a mathematical function? It's something, when you put the same input, you always get the same output. That's the definition of a mathematical function, well, informal definition of a mathematical function. So, for example, a signal is a mathematical function. You give it the time, a point in the time, for example, at sample 10, and it gives you the value of the sample at time 10. Whenever you give 10, it gives you always the same sample. So, a signal is a mathematical function, a function of time. When you do signal processing, you are operating on signals. So a signal processor is a mathematical function on signals that are themselves mathematical functions of time. So in Faust, you describe a signal processor starting for elementary signal processor. For example, plus is a signal processor that takes two input signals and produces one output signals by adding together the samples of the two input signals. Again, it's a mathematical function. In Faust, you program by combining elementary signal processor like plus, for example, multiplication, etc. And you combine them by an algebra of 5 operations. We saw the colon sign. So this is one of the 5 operations of the algebra of Faust, a way to combine things together. So you can think of this algebra of operation as 5 different ways to combine audio circuits, so to speak, signal processors together. Faust is heavily based on this idea of programming by composition. You take two things, you combine them together to create a more complex thing. So the other point, as I mentioned, is that Faust is compiled, but it's compiled in a smart way, so to speak, in the sense that even if you give two different Faust programs, but that have the same mathematical meaning, then the compiler is supposed to create the exact same code, the most efficient one. So you are, in principle, never penalized, how do you say, penalized of using a very structured way, a very clever way to program, very clear way to program, which is not the case when you program in C or in C++. You have a penalty in these languages when you structure your code, so to speak, which is a shame, but that's the reality. It has a well-defined and preservable formal semantics. Maybe that's something that I can show you. We all have a problem doing electronic music of a problem of preservation. How are our work going to survive? In particular, it's not enough to preserve the files, so to speak, because the languages evolves. For example, if you take a C program that was wrote maybe 10 years ago and you try to compile it on a modern computer, you are going probably to have warnings and maybe errors. And so it means that you always have to readapt your code to keep it alive, so to speak. It's not enough to preserve the files themselves. That's a big problem. So in Faust, we solved partially the problem by doing mathematical preservation. The idea is that you can take any Faust program and you can make automatically, without writing any line of code, a mathematical description, an exact mathematical description of what your Faust program is doing. So the idea that mathematics is a more universal language than Faust, it would last for centuries, so it's very reasonable to think that the mathematics, even especially simple mathematics like signal processing, will be understandable maybe in 1 or 2 centuries, while Faust programs probably won't be understood anymore because have gone, so to speak. So mathematical preservation, it's very important. Let me make a quick demo of mathematical preservation. Okay, so let's do a simple Faust program. Let's look at the diagram here. Let's do plus, followed by absolute value, followed by square root. Okay, so here the graphical representation of the program. Now I'm going to export that. I'm going to use mix and mathematical documentation, compile. So this Faust program is sent to the server where we're going to generate a mathematical description on what this program does. So here the program is very simple, so the description will be also very simple. But you will see that this description doesn't use Faust at all, just use pure mathematics. The idea is that it's a kind of mathematical picture of your program, and maybe in the future you can take this mathematical description and just re-implement it in a completely different programming language and have the exact same result. At least this is the idea of this preservation. So we can download that, save, replace, show in Finder. Here it is. And now we have a PDF here. And this is, and voila, this is what we generated. And it gives you a mathematical formula that describes what we were computing. So we were adding the two input signal, taking the absolute value, the 2 bars, and taking the square root of this. So this is done automatically. And this can be done because Faust has a very precise formal semantics. We know exactly at the sample level what any Faust program is doing very precisely. Okay, so let's go by here. So well-defined preservable formal semantics, just what I illustrated, and easy deployment. So easy deployment means that for the same Faust code, we can deploy to the web, to Android phones, iOS, embedded system, etc., etc. So as I mentioned, Faust is based on a purely functional approach. So maybe we can skip this slide, but it just explains that a signal is a function of time. A signal processor is a function on signals. It transforms a group of input signals to produce a group of output signals. The Faust algebra of function composition is based on 5 operations: the split, merge, sequential composition, parallel composition, and recursive composition. So this afternoon, we will study all these operations because this is the way you build Faust programs. They are not very complicated. The most complicated one is the tilde operation, which create cycles, loops into the circuit, so to speak. So it's important when you want to create feedbacks. Okay. So here are some examples of Faust elements. So numbers, for example, are a signal processor, so to speak, that don't take any input signal and they produce a signal, like 1 produces a signal which is 1, okay, at every time position. We have button, sliders, etc. And then you have all the mathematical operations that you usually have on numbers, but you have them on signals. So if the multiplication, instead of multiplying 2 numbers, multiply 2 signals by multiplying the samples 2 by 2. There are some specific operations. We will see the at operation, which is the delay line, the delay operation, which is specific to Faust because it's a time-based operation. So you don't have that in C, for example. All the operations that you have in C, you have them on numbers, you have them in Faust on signals. And obviously you have user interface elements. sorry. The user interface elements are a very abstract way to describe the user interface. You say, okay, here I would like a slider that go between 0 to 10, for example. Here I would like a button, a checkbox, etc. And the interpretation of these user interface elements is done by what we call the architecture file. I will describe in a moment what architecture files are. For example, on the OWL box, the white box we saw, there was buttons. So obviously you don't have a graphical user interface, but there is a mapping between the sliders and the buttons that is done automatically. The same is true for the sliders on an Android, on an iOS phone. You will be able to map the accelerometer to control the sliders, for example. So let's go into more details on the block diagram algebra. Who recognize this picture here? Okay, it's a Moog synthesizer. And this one, do you know which synthesizer is it? Well, it's not a synthesizer, it's the ENIAC, which is considered the first electronic computers in 1945. What's interesting is to see that the way it was programmed is the same as the way as you program a modular synthesizer, by combining operation, by connecting the output of one operation to the input of another operation. So just to say that programming by patching is very natural to musicians, but it's also rooted to computer science somehow, because the first computers were programmed that way. Okay, so Max Patch, who wrote that patch? Oh, I won't tell the name because, okay, it will not be very fair. But you can, with Max, you can do this kind of very complex and unreadable patch. In Faust, it's not really possible because you have this block diagram approach that makes always things very structured. Okay, so we have 5 operations. These operations have priority, so it's important to know the priority of operations. The highest priority for the recursive composition, then you have the parallel composition, the sequential composition, the split, and the merge. To the algebra to be complete, you have 2 special signal processors, so to speak. The exclamation point is called cut, and it's something with 1 input and no output. So it's used to terminate outputs that you don't want to use, so to speak. And the second one, using the underscore sign, it's the wire. From a mathematical point of view, it's the identity function. So it's something, a box, that takes 1 input signal, produces 1 output signal, and the output signal is the exact same as the input signal. So it's like a perfect wire. Okay? So for example, if you want to create a stereo wire, you can use this underscore sign combined with a parallel composition and another underscore sign. So underscore, comma, underscore will be a parallel a stereo wire. Okay, so the simplest composition operation is the parallel composition. So imagine that you have audio effects. You create a rack of, you stack all your audio effects. They are not connected, they're just stacked together. So you have a super audio effect with many inputs and many outputs now. So there are no constraints on how you can stack a signal processor together. Then you have the sequential composition. So for example, here you have a parallel composition of a multiplication and a division, which is represented here, and you connect that to an addition. You can do the connection because the outputs of A has two outputs, okay? The output of the multiplication and the division, and the addition operation has two inputs, so you can connect them together. So this is a valid Faust program. Is it clear? Well, it's a little bit abstract, but once you start to practice, it's going to be better, so to speak. Then you have the split operation. It's like using wire, so to speak. So you have maybe a stereo output, and you distribute the stereo signal to your rack of effects. So the constraint here is that the number of inputs of the rack of effects must be a multiple of the number of outputs of your source, your sources. Okay. So here we have 6 inputs. It's a multiple of 2, so we can do the split connection. The reverse of the split connection is called merge, and here it's like you merge on a stereo bus all the outputs of your rack of effects, so to speak. So in this case, the number of outputs of A must be a multiple of the number of inputs of B, and this is the way they are connected. So imagine that you have a rack of stereo effects and you have a stereo connected to a stereo device. Then all the left channels are added together, all the right channels are added together and feed the left and the right channels of the B equipment. And then you have the recursive composition that allows you to create cycles. And it's by far the most complex one. Basically, it takes 2 circuits, A and B. So you draw the A circuits here, you take the B circuits, draw it reversed on top of A, then you connect all the inputs of B to the corresponding output of A, and all the outputs of B to the corresponding input of A. It's more or less like this. It's a little bit more complex, but we will see that in a moment. Okay. So here it's an example of a delay. And this is what we are going to code now with using the online editor. So it should be clear if I code that in front of you. So you know, usually it's not a good idea to do live coding. It should go wrong at some point, but hopefully more at the end than at the beginning. So here, instead of you doing something that produces signal, I'm just going to do something that transforms signals. Okay? So you will see the block diagram. Let's start with a simple plus here. Now, I'm going to use tilde to connect, to do that. So you see plus, tilde, underscore. So underscore is the wire. So there is no box drawn around the wire, just a wire. So what we say here, that we connect the input of this wire to the output of plus, and the output of this wire to the input of plus. The outputs of plus, tilde, underscore are the output of plus, and the inputs of plus, tilde, underscore are the input of plus that are not connected to an output of underscore, of the wire. Again, it's complicated. Why it's like this? Because like this it works and it's convenient, even if it's a little bit complicated. So here and you see here we have a small white square. This white square represents a one sample delay. This one sample delay is automatically introduced by the tilde operation, just to make things computable. So what this circuit does, it does an integration. It's an integrator. So the output signal is the previous output signal plus the input signal. So if I feed this circuit with 1, it will produce 1, 2, 3, 4, 5, etc., etc. Okay. So it's an integrator. So what we want to do here, instead of just using a wire here, we want to make an echo. So we want to delay more than just one sample the output signals, and we want to multiply it by some feedback coefficient. Okay? So I will start by writing that with hard-coded values, and then we will see how to introduce sliders. Okay? So we're going to make this echo, and then we will try it on the editor, and then we will export that as a VST plugin, and we will use that in Reaper. Okay? That's the plan of the demo, just in case it fails, so you know what I wanted to do. Okay, so we're going to replace this underscore. So let's open parentheses here. So what we want to do, the first step is we want to delay the signal. So we're going to use the at operation, and we will give the amount of delay in samples. For example, 10,000 samples. Then we want to multiply the signal by some value, for example, 0.75, which is our feedback coefficient, so to speak. And here is our echo program. Okay, just one line. Now we can try it. Here we need an input to see our program in action. So we can use an audio file. There is a predefined audio file. You can drop any audio file that you want, and we can try it. So let's run the program. Okay. So now we would like to transform a little bit our program to make it a little bit more sophisticated. So the first thing we are going to do is to rename this echo. We can do that and then write process equal echo. Okay? So it's exactly the same program than before. Why I do that? Because now I want to introduce parameters in my echo. So instead of having hard-coded 10,000 samples and hard-coded 0.75 as a feedback coefficient, I want to put two variables. So this is a very important operation when you program, which is to abstract things. So I'm going to copy that so you can see what I'm doing. And I'm going to comment this line here. And here I introduce two parameters, called them D and F, D for delay and F for feedback. And I'm going to replace here 10,000 by D and 0.75 by, by F. And now I'm going here to use echo, but now echo needs two parameters. So I'm going to use echo and give the actual value for these parameters, okay? So here, again, 10,000 and 0.75. So here I should have exactly the same behavior than before. And as efficient also, because the mathematical meaning is exactly the same. Okay. Now I would like to change this value here and to put a slider between 0 and 1. So I can use a horizontal slider, H slider, and the slider takes several parameters. The first one is the name of the slider as it's going to appear on the user interface. So it's a string, I can put whatever foo. No, maybe foo is not a good idea, feedback. Then the next parameter is the default value of this slider. When we start the program, what will the value delivered by the slider without any action of the user? So by default, we can say 0. Then we should give the minimum and maximum values of the slider. So the minimum value can be 0, and the maximum value is going to be 1 or 0.99. And then we give a step value, for example, 0.01. Okay, so you see now we have a user interface with a slider, so we can run that. Okay, so it works. Horrible clicks, sorry. So I would like to introduce another parameter, which is the amount now to control the amount of the delay. So I can just replace 10,000 by a slider again. I call that delay. The amount of delay, the default is going to be 10,000. The minimum 0 and the maximum maybe 40 for 1 second. Well, it depends of the sampling frequency, but let's do that simple. Now we have 2 sliders. Okay, so we can. Okay, let's call that, because we're going to create a VST plugin, sometimes it's useful to add some what we call metadata, for example, to declare the name of this plugin. So we can declare name my super echo. Okay, and I'm going to give a name to this file here and call that my super echo also. Okay, we can remove this. And I can export that to a VST plugin. So I choose OS X, I choose VST, and I click on compile. After a while, no, it's okay. So I can just, is it okay? Yeah. Can download the code, save, replace, show in Finder. Okay, so you see here we have the VST plugin. So I'm going to place this VST plugin into my, where I put all my VSTs. And now I should be able to run, should put my glasses, sorry. Okay, so I'm going to start Reaper. Yeah, I'm still evaluating. Okay, I have a very simple sequence here. So I would like to add an FX, and in my VST, I should see my super echo. You see, it's here. And we see the sliders. Okay, so we can try it. Okay, so we don't have feedback here. Okay, so that's all for Reaper now. Let's go back to the slides. Oops. Okay, so let me add some more details about the design of Faust, and the main goal are to combine expressivity with performance with deployment. Maybe I'm going to skip a little bit these details. Well, if you are familiar with, maybe, yes, let's explain something, which is to this. Okay, this is complicated code, so don't look at it just, but this is the description of a fast Fourier transform. And it's a description, it's a recursive description. Just to say that in Faust, like in Max, you can create a patch. Max is graphical, Faust is textual. But the difference is that in Faust, you can create a program that generates the patch. You have the power, the expressive power of a programming language to describe how to produce the circuit, so to speak, how to generate the circuit. So here it's a way to describe an FFT. And here you see a parameter n, which is the size of the FFT. You can use this FFT with parameter 1, just a one sample FFT. We have two cables because are complex numbers. Okay. Here you can create an FFT of 2 with the same program. FFT of 4, 8, 16, 32, and 64. So you see that, okay, if it's FFT of 2 or 4, it's okay if you do the connection manually. But when you start to have very complex programs like this, it's much more convenient to have a programming language to build and generate the circuit. So it's important to understand that in Faust, you can manually describe the circuit, but you have all the expressive power of a programming language, to generate the circuit itself. So you can describe high-level concepts. For example, the concept of dry, wet, whenever the FX is. Can you just describe, okay, I have some reverb and I add the feature dry, wet on top of it, okay, because you can program that. Okay, fully compiled, blah, blah, blah. Okay, so if you want to look at, so this is a very simple Faust program. Now you know underscore, you know the comma sign, so we have the two stereo cable. We have a split operation, an addition, and a subtraction. So it means that on the left channel, we add the two input channels, and on the right channel, we subtract the two input channels. And this is the C++ code generated. Okay, if you are familiar with C++ or normal programming language, you understand what's going on here. You see that we take the two input signals and we add the samples together, we subtract them to produce the output, the first output and the second output. So the code generated doesn't depend on any library. We just generate plain C or C++. So you can use Faust to implement signal processing libraries, so to speak. Okay, so this is an example of we will see that this afternoon, how to generate a Sawtooth signal. So here you see that we have a kind of integrator, but instead of just doing the integration, we use a modulo operation so that the output value will never exceed 1. Whenever it goes up to 1, it goes back to 0. Okay, so we increase the samples, we increase the value one after the other, but because of this modulo operation, we never exceed 1, and we do a Sawtooth signal by this way. It's going to be more clear when you will practice this afternoon. Okay, so this is an example of what I was saying, that when let's say that you have this process here. So on this channel, you multiply the signal by 0.5, then you add the delay of 2 samples. Here you add the delay of 1 sample multiplied by 0.5, and then again take a delay of 1 sample. From a mathematical point of view, this is just doing a 2-sample delay on the input signal. You made that very complex, but it's just a 2-sample delay. And the Faust compiler will be able to discover that and just compile the code as a 2-sample delay. That's very convenient. Why? Because when you use Faust into a creative way, like I mentioned at the beginning, you often reuse code by others. So you don't know what's inside the code. Maybe you would take let's say a 4-channel reverb and feed the 4-channel with a stereo signal only. The Faust compiler will discover that and will do all the simplifications. So no matter how complex you combine things from existing piece of software, what will really run is the mathematical equivalent of your program. And so you can really structure the things very, very detailed, put a lot of parameters, but maybe instead of choosing putting sliders, you put constant value, and the compiler will do all the computation that can be done at compile time, so that the computation done in real time will be only minimal. Another interesting point, we won't see that much today, but the fact that Faust is able to do automatic parallelization. So you know that since 2004, the the speed of the microprocessors more or less stopped to grow. Now we are about 4 gigahertz for a processor. What started to grow again, what continued to grow, was the number of transistors you can put on a chip. So the designers of microprocessors start to make multi-core microprocessors. So the speed doesn't double anymore every 2 years, but the number of core, now it's number of core that double. So now we have a GPU with many, many cores, for example. The point is that it's more complex to exploit all the processing power that you have when you have a multi-core machines, because you need to discover all the computations that can be done in parallel. And so in Faust we have quite efficient parallel code generators using either a standard called OpenMP or our own scheduler based on the idea of work stealing scheduler. Well, okay, so it means that you can use this to exploit the fact that you have a multi-core machine. So here it's an example of a sound installation I did several years ago, and you see the gain of performance you can have by running in parallel mode this Faust application here on the 8-core machine. You don't multiply the performance by 8. It's very rare when you can do that, but you can, here in this case, multiply the performance, I think, by 6, something like that, which is quite good. And doing manually parallel programming, it's quite a complex task. Again, it's useful to have the Faust compiler to be able to do that for you. So easy deployment. Okay, so we already saw that. The point is, if I wrote a reverb or a sound synthesizer in Faust, and I want to use it in Max or in Pure Data or in Supercollider, I don't want to have anything to change. I just want to take the code and run it, deploy it like this. In order to achieve that, in Faust you have a clear separation between two things. The computation core, so to speak, and the environment, and the way you connect this computation core to the external world, so to speak. And this is done by the concept of architecture file. So an architecture file is basically something that indicates how to use the audio drivers and how to build the user interface. So the Faust code itself has a description of the user interface. You saw horizontal sliders, for example. But they don't tell how they should look like, what kind of SDK you should use to that. Is it going to be Mac sliders or whatever slider? This is the role of the architecture file. So the Faust code just gives an abstract description of the user interface, say, okay, I need this slider. Whatever interpretation of this word should be is done by the architecture file. So you may have an architecture file that runs on the OWL, the small white box, doesn't have any graphical user interface, but it interprets sliders as the 4 knobs it has. Or you can have something that runs on the web, and or that use OSC messages, etc. So by doing like this, you can really separate the computation core from the way you are going to control that computation, or the way you are going to produce the samples and receive the samples. So the architecture file indicates how we are going to connect this computation core to the external world. This connection means how we are going to connect to the audio interface, and how we are going to connect to the graphical user interface. So by doing this separation here, we can deploy the same code on many, many platforms. As you saw, we can deploy it on Android, for example, on VST, on Macs, Supercollider, etc. So these are some of the platforms that are supported. For example, for user interface, we can have a graphical user interface, but you can have a MIDI interface or MIDI interpretation of your abstract user interface, OSC interpretation, and HTTP interpretation. For example, you can use Faust to program a Raspberry Pi effect and using an HTTP interface. So it means that you connect from a remote computer to the Raspberry Pi. You see it will appear as a web server. You connect to that web server and you see in your browser the user interface of the code running on the Raspberry Pi, and then you can control it remotely. That's very useful, for example, if you do a sound installation. You may not want to have a full computer running the sound installation, but something where you can remotely connect to this box and control for, or even give users the control via appropriate an appropriate address. Another important point is to be able to compile Faust everywhere. So we have compiler that you can install like a traditional compiler on your machine, but you may want also to embed the Faust compiler. We saw on the web browser here, the Faust compiler is embedded into the browser. On Faust Live, it's a C++, it's a Mac application. Well, not only Mac, it's an application that embeds the Faust compiler. This is possible thanks to a technology called LLVM, which is a modern infrastructure for writing compilers that are now used almost everywhere. For example, all Apple compilers are based on LLVM. You can use WebAssembly, etc. So we have developed a library version of the Faust compilers. This library version exists in two flavors, so to speak. One which is native code, and you can embed into your C++ program. And the other one is a JavaScript version of the library, and that you can embed into your browser. That's the case with what we're running on the demo. Okay, so let me show you some of the, how much time do I have? A few minutes. Let's show you maybe FaustGen, which is the Faust compiler embedded into MaxMSP. Okay, I'm not really an expert in MaxMSP programming, so I'm probably going to be slow. So I'm going to show you this FaustGen, and then I'm going to show you maybe I'm going to start with this. Faust Playground. Faust Playground, it's a kind of simplified graphical playground to program Faust programs. And it was designed for kids, essentially. But it's also useful for adults like us. So I'm going to switch to where is the Faust Playground? Okay, so this is the Faust Playground. And so you have a library of pre-existing stuff. For example, let's use that. And then you can connect this module. Okay, maybe I'm going to add some effect like an echo. Okay, once you are happy with your code, you can export it. But let me show you that you can, so you have predefined modules, but you can also use any Faust code that you have. This is what I would like to show you. Clack, demo Faust playground. Okay, so it's a module. And another one like this. So I'm going to connect. So basically they are just what we saw just before. But you see now the slider here are white. So what you can do here is that you can edit the mapping. So we're going to export that as an Android application. And if you want to control the sliders, you can control them manually, obviously with your fingers, but you can also connect them to the accelerometers. And this is what you have here. For example, you see that this value, the brightness, is controlled by the x-axis of the phone. And you can choose the curve and the mapping and control all these details here. Let's assume that the way they are mapped, it's okay for us. Now I'm going to export that. So let's rename this patch here and call that application my super app. Here I have the same export system that we saw previously, but because it was designed for kids, the detail of exporting on Android is hidden, but you can obviously saw that. And then you click on export. So again, the code is sent to a server, and we will end with a QR code. Now you can take your phone, Android phone. You need to have a QR code reader, and okay. So let's. Okay. Okay, so now something strange is happening. Okay, for some reason this code doesn't work. That's the demo effect. Fortunately, it happens really at the end of the talk. And fortunately, I should have this example ready to run here. Okay. this is what exactly the same code here. Let me turn that off. I don't know if you can, no, probably you cannot see, but so I have my 3 slider I can control here. And the amount of feedback is controlled by the accelerometers. So here I have a mixture of gestural control and finger control. Okay, so I will investigate why this one was not working. Maybe because well, I don't know. Okay, let's go back to the, oh yes, do we have time still, or? Do we have 5 minutes more? It's okay for you? You survive 5 minutes more? Okay. So I show you quickly how Faust Gen works. Okay. So let's go back to quit that and go back to Max. Okay, so here we had the still running. Oh, doesn't make any sound. Maybe because. Okay, so I'm going to use FaustGen to create an echo inside Max directly. So I put in edit mode. I add an object called FaustGen. Okay. Oh. That's strange. The patch disappeared, more or less. Ah, okay, that was unexpected. Okay, so the way it works is that once it's running, you can edit the Faust code inside here. Let's do the djembe stuff. Check here, it's just copy this code into if I close this, oh, very strange. Yes, okay, sorry. I'm not very Max fluent. Okay, so if I connect these two outputs here and here, okay, so it's compiled on the fly, and it's very convenient. So let's add another FaustGen box. Okay, you can just remove this one. And I want to connect the output of this one to the input of this one. Okay, so if I... now we don't have the button anymore. So we should put a message. I don't remember what are the messages. I guess if I put play 0 and another one play 1, should work. Second demo effect. Well, it works very well once you know how to use it properly, but since I'm not using Macs very often, sorry for that. No, because you need to send a message, which is a user interface message. Let me edit the code here. No, okay, it's called djembe, so let's rename that play. And the name of the button should be the name of the message, obviously. So if I close that, okay, now it works. And obviously I could add the echo code here in the second Faust gen. Okay, just to conclude quickly, if you want to learn more Faust, well, there are several places where Faust is, you can learn Faust. For example, at Karma at Stanford University, at Menus, Louisiana State University, and Aalborg in France at Université Jean Monnet. There is a master program for RIM, computer music producer. You can learn it also at IAM, at IRCAM, and in Paris 8. And there is an online course on Cadenze, so you can register on that course. It's free if you don't want to have credit for Stanford. So it was a course which was financially supported by Stanford University. And last but not least, you have the Faust website where you have many tutorials and documentation. Voila, thank you very much and sorry for the demo effect.